in this video series I did a dilution accretion problem, and I probably call it the well-stirred tank problem, and which is what is often referred to. Our book calls it dilution accretion, and I'm around page 125 in case you're wondering. So it might be a good idea for you to go back and rewatch that early video as a very basic example. The problem I'm going to do is a little more complicated and I think pretty interesting. And so this is on page 125 and it's problem number 6. So I'm going to go ahead and read it. It says, a tank initially contains 100 gallons of brine whose salt concentration is 0.6 pounds per gallon. Brine, whose salt concentration is 1 pound per gallon, flows into the tank at a rate of 2 gallons per minute. The mixture flows out at a rate of 3 gallons per minute. So it says find the salt content of the brine and its concentration at the end of 60 minutes. And then they give you a hint, after 60 minutes the tank contains 40 gallons of brine. Well, yes, of course. Because if you think about it, we have 3 gallons per minute coming in, 2 gallons per minute coming in, 3 gallons per minute coming out, so the net is 1 gallon of water solution going out every minute. So after 60 minutes, we've declined from 100 gallons down to 40 gallons. Well, so there we go. I think it's a pretty interesting problem, and let's give this a shot here. So, first of all, we need a function. What are we trying to solve for? And I propose that we let y of t equal to the salt after t minutes. All right, and now our tank, and I like to draw these little pictures. I don't know if this is all that helpful, but here's our tank, and initially contains 100 gallons. We'll deal with that in a minute. But water is pouring in at 2 gallons per minute. And the concentration of that water, or they call it brine, is 1 pound per gallon. 1 pound per gallon. So in terms of salt, the salt is flowing in at 1 pound per minute. Well, and this incidentally influenced me why I wanted to write my function this way, because I have salt coming in at 2 pounds per minute, and the rate of change of this ends up being in units pounds per minute. So I'll explain that in a minute. All right, now coming out of the tank, at the same time, if the water is flowing at 3 gallons per minute, 3 gallons per minute, and what is the concentration of the brine coming out? Well, it would be y pounds of salt in the tank divided by the amount of water in the tank. Well, that poses a new problem, doesn't it? How much water is in the tank? Well, it turns out to be 100 minus t. So we have y pounds per 100 minus t gallons. As you can see, the gallon units cancel. I have pounds per minute. So let me explain that. If it's not terribly obvious yet, the amount of water in the tank, the amount of water has to be 100 minus t gallons. Now why is that true? Because we start off with 100 gallons, and every minute we lose 1 gallon of water. And so after 1 minute, it'll be 99. After 2 minutes, we'll have lost 2 gallons of water. It'll be 98 gallons. So the amount of water in the tank is simply 100 minus t. So that means the concentration coming out is the amount of salt in the tank, y pounds, divided by the amount of water, 100 minus t times gallons. And these cancel, so it says that the concentration coming out of the tank is 3y over 100 minus t pounds per minute. All right, so these are important considerations. And so let's see if we can set up our differential equation now. So you might think of it this way. The rate of change of salt will equal to the salt coming in minus the amount of salt going out. So remember, this is a rate of change. The salt is changing according to this little formula. Now, salt comes in, salt goes out. That's the rate of change. And again, the assumption is that as soon as it enters the tank gets, stirred very well. So immediately the concentration of the tank is constantly changing through time. That's not terribly realistic, but it's close enough, I think, to make it a great problem. All right, well, so I think this is where you begin to set up differential equations. If you can put in words involving rate of change, then you've created a differential equation. Because what is rate of change? It's the derivative. The rate of change of the salt is the derivative of the amount of salt with respect to time. dy dt. So rate of change in salt with respect to time. And the units of this are pounds per minute. Pounds per minute. Because y units are pounds of salt. And I probably should have put pounds here as my unit. And time units are minutes. Now, the amount of salt coming in, it's coming in at 2 pounds per minute. So 2 pounds per minute minus the amount of salt coming out, and it's going out at 3y over 100 minus t, 3y over 100 minus t pounds per minute. So I probably should have written pounds per minute here, but the units absolutely have to match here. If I don't have pounds per unit here, here, and here, then the equation is just worthless. Okay, those units have to match up across the equation. Well, there we go. Because we have the units settled, we have the equation settled, let me do some erasing, and we'll write the differential equation. And I have one other thing to add to it. We have an initial condition which I haven't yet accounted for. So here's our differential equation from down here. Y prime equals to 2 minus 3y over 100 minus t. Now, we also have an initial condition, don't we? The book says that initially we have 0.6 pounds per gallon concentration. And initially we also have 100 gallons. So the initial amount of salt is 60 pounds. So the initial condition here then is the amount of salt. Remember, y represented pounds of salt in the tank. Y prime represents pounds per minute, the change in salt per minute. But y itself is just pounds. So the amount of salt in the tank, and when time is 0, would be 60 pounds. So there's our initial condition. Well, I think everything is set up for us to solve. And let me do some erasing here. And looking at this, it looks like what we've been doing lately in these videos. I'm going to bring this term over to the left side. We have y prime plus 3 over 100 minus t times y equals to 2. So this looks like one of those equations where we would use the integrating factor to solve. And my integrating factor would be, it is because we have the derivative plus function of our independent variable times our dependent variable equals to a function of the independent variable x. And I realize too it's just a constant, but it's still, you could think of it as a function of x. So the integrating factor will be, that's e raised to the integral of 3 over 100 minus t dt. And let's see, this is a logarithmic form. It's like a dt over t form. And what would it actually be? It would be e to the, I believe it's going to be negative 3 natural log absolute value 100 minus t. So is that correct? Let's check it. If, ignoring the e here, if I were to take the derivative of this part right here, I have negative 3 times 1 over 100 minus t times the derivative of 100 minus t, which is negative 1. So this negative would cancel with that negative, leaving a positive. So that's the correct integration. And if we look at this as e natural log 100 minus t, and everything is raised to the negative third power, then as is the case, e raised to natural log all cancels, they're inverse functions, absolute value cancels, so we have 100 minus t to the negative third power. So now what was that? That was our integrating factor, wasn't it? So I'm going to do a little erasing and write this, multiply this equation by the integrating factor. So here's our equation. That's the integrating factor we multiply by. And this gives us y prime times 100 minus t to the negative third power plus, and here this is a, think of this as a minus 1 power, or as this as 1 over 100 minus t raised to the third power. So anyway, this ends up being a fourth power. I have 3 times 100 minus t to the minus fourth power times y equals to 2 parentheses 100 minus t to the negative third power. There we go. Yeah, it's kind of a mess. But it turns out this whole left side, if all went well, will be the derivative with respect to time of our variable times the integrating factor. Well, let's make sure. So if I took this derivative with respect to time, I would get y prime times this factor plus negative 3, 100 minus t to the negative fourth power, and then chain rule, this derivative is minus 1, cancels that negative 3, so that's positive 3, times the other factor, y. And so we can separate the variables here. Differential of this mess, 100 minus t to the negative third power y, is equal to 2 parentheses 100 minus t to the negative third power dt. And then we can integrate. So this is kind of a messy problem. Now there are some other ways to approach this. You could do a change of variables up here if you wanted to. For example, if you let 100 minus t be equal to u, then I'd be multiplying by u to the negative third power. This would be 3 over u. It might be a little easier to work through. I didn't change my variables, so I'm left with a bit of a mess. But there are other options in working with these that may end up being a little easier. Okay, so let's see if we can finish this up here. I'm going to do some erasing. So I took this bottom here. When I integrated the left side, I just simply got that part right here. Integrating here, it ends up being parentheses 100 minus t to the negative 2 plus my additive constant when we integrate the right side. So let's verify that. When I take this derivative, it's going to be negative 2 parentheses to negative 3. I almost have that. But then chain rule, this derivative is negative 1, canceling that negative, positive 2. So that's the correct integration there. And then I think it would be advantageous for us to solve for y. So I'm going to multiply all this stuff by 100 minus t raised to the positive third power. So that's going to clear out our negative exponents and also just leave with a y. So my left side is y, and y is a function of t, so I could write that as y of t equals to, so here I've got a negative 2 power times something to the positive 3. That leaves a first power, so I have 100 minus t to the first. I just write that as 100 minus t plus constant times 100 minus t cubed. All right. So let me erase this. And at this point, I think we can plug in our initial condition. Y at 0 equals to 60. So y will be 60 when t equals to 0. So 100 minus 0 plus c times 100 cubed. So if we solve for c, this is, that 0 goes, of course. I'm going to subtract 100 minus 40 and divide by 100 cubed. It's equal to c. There we go. Now that means that c is equal to negative 40 over 1 followed by 6 zeros, 1 million. So 100 cubed will be, this is 10 squared cubed is 10 to the 6th power. We can cancel that. And how about we write this in scientific notation? This is negative 4 times 10 to the negative 5th power. So that's one way to handle that constant c. Well, so now we can write our function. The amount of salt in the tank, y of t, will be 100 minus t, and then c is a negative number, so this is minus 4 times 10 to the negative 5th power times 100 minus t cubed. So there's our equation that describes the amount of salt in the tank after t number of minutes. Now, the book also wants to know about concentration, and we know what how much water is in the tank. So if we just divide the amount of salt by the amount of water, we'll get the concentration. All right, so the first question was, how much salt is in the tank after 60 minutes? All right, so y at 60 minutes will be 100 minus 60 minus 4 times 10 to the negative 5th power times 100 minus 60 is 40 cubed. So I'm going to run that through my calculator. And let's see, 100 minus 60 minus 4 times 10 to the negative 5th power times 40 raised to the 3rd power is 37.44. 37.44. So that's the pounds of salt in the tank. Now, after 60 minutes, there are 40 gallons in the tank. So the concentration would be 37.44 pounds divided by 40 gallons. And let's see, that would be 0.936 pounds per gallon. All right, well, if you're my student, I'm going to expect you to write a sentence or two. So after 60 minutes, there is 37.44 pounds of salt in the tank with a concentration, that comma probably doesn't need to be there. I tend to write too many commas. With a concentration of 0.936 pounds per gallon. All right, so let's check the book. I think that's right too. I'm feeling pretty good about this one. Okay, 37.4 pounds and 0.94 pounds per gallon. So they rounded off to 1 decimal place, which is probably realistic because the tank is not perfectly stirred. You know, these numbers would be exact if the instant brine going to the tank gets stirred in the whole concentration, so that when it drains out, it has the concentration at that instant. If that was actually true, then these numbers would be exact. But it's not quite true in reality because it takes a little while for everything to circulate through the tank, no matter how well you stir it. But this is pretty close to reality, I imagine. So, okay, I'm going to do one more of these problems. With this time, it's going to involve 2 tanks.